Hi folks, welcome back to Physics with Captain Rod. I'm making this video to provide an example of how to apply Newton's laws in examples of circular motion. So what we're looking at here in this example, we've got this 10 kilogram mass hanging at the end of this 5-meter long rope, which is attached up here somewhere. And this is swinging back and forth, right? And this is an example in physics of what we call simple pendulum. So it's swinging back and forth in such a way that on the endpoints it makes a 40-degree angle with the horizontal here and here. So you got to imagine this thing swinging back and forth. And what we're going to do is we're going to try to calculate the maximum tension in this rope. So hopefully your gut instinct will tell you where that tension is going to be a maximum. As this thing swings further and is moving faster and faster and faster, the tension in this rope would be increasing. And the rope is going to have a maximum tension when it's at the bottom, when this mass is here at the bottom of its motion. So what I'm going to do is I'm going to draw a free body diagram of that object at this location. So first I'm going to, actually, I think I can just, there we go. I already had that set up. All right, so I'm going to imagine this object right here. And again, it's important to realize that at that point in time, this object is moving to the right. And what I'm going to do now is I'm going to draw all the force vectors acting on it when it's at this location. Right? So as this object swings through this location, at this instant in time, there's going to be a gravitational force down, mg. And the rope, although I don't have it connected in the picture, you got to remember it is still in fact connected, and that rope is going to apply a tension acting on this object, and that force vector is going to point up. Oops. How about T for tension? Now you'll notice in the picture I have drawn this force vector larger than this one. I'll kind of explain why. So this thing's undergoing circular motion. At this point right here, the velocity vector is changing direction. So because it's moving in circular motion and the velocity vector is changing in direction, I know that there's going to be a centripetal acceleration. And centripetal acceleration is always directed towards the center of curvature, which is here. So the acceleration direction at this instant in time is up. Right now I'm going to go ahead and write a Newton's second law equation for my free body. Sum of all forces equals ma, up positive. Now, why did I decide up positive? Because of my observation here that the acceleration direction at this instant in time is up, because it's a centripetal acceleration directed towards the center of curvature, and my standard rule of thumb is to identify the acceleration direction, call that positive. Another thing to consider in this picture, this vector that I just drew is an acceleration vector. It's not really part of the free body. It's not a force. The only forces acting on this mass are its weight, which I've put in here, and this tension. So now we go ahead and write a Newton's second law equation for this. Sum of all forces equals mass times acceleration. So when I look at my free body, the tension is up, the mg is down, so the net force is going to be T minus mg. Now, right hand side. A mistake I see a lot is to try to say that this free body is somehow balanced and these forces are equal, and therefore they add to zero. And that's just not the case. This thing is in fact accelerating up. At the instant shown, the velocity vector is this way. If it were not accelerating up, that velocity vector would stay constant. This thing would just go in a line. All right, so it's accelerating upward. So we're going to have m times a, and I'm going to go ahead right now and put v squared over L for the acceleration. Here's why I did that. Centripetal acceleration in general is calculated by v squared over r, where r is the radius of the path it's taking. The distance from here to here is essentially equal to the length of the rope. So that's why I put L in that location. Now this equation can be solved for the tension no problem just by adding mg to both sides. So we're going to have mg plus mv squared over L. But now the million-dollar question is, what do we do about the v squared? So you'll notice that as this thing moves back and forth, the potential and kinetic energy of this object is constantly changing. So what I'm going to do is I'm going to use the work energy theorem to try to find this speed here. I'm going to call this position 1, this position 2, and I'm going to write out a work energy theorem. Right, PE1 plus KE1 plus work equals PE2 plus KE2. Now, anytime you're dealing with potential energies, you have to define a datum. And usually the way I have people pick a datum is the lowest point in the diagram, but not always. This one I'm going to break from that a little bit. When doing these circular motions, I like to use this line as a datum. I'm going to go ahead and do that. I'm going to put this in blue. So for this problem, this is going to be my datum. So now there are potential energies under both the PE1 and the PE2 term. Furthermore, the potential energies are negative because we're below the datum. Right, so the PE1 term is going to be minus mg, I'll just say h for now, where the h is going to be this distance right here. Now, from this triangle right here, the hypotenuse of this triangle is equal to L, the length of the rope. So this height is opposite the 40-degree angle, so its magnitude is L sine 40. So I'm going to go back now and put L sine 40 right here. So this is now going to read, whoops, I guess what I'll do is just rewrite this. Minus mg, and then the h is equal to L sine 40 degrees there. Could have just left it minus mgh and handled it later, but it's handled now. Minus mg L sine 40. All right, kinetic energy. At the end point, it's not moving, so its kinetic energy is 0. Work term is 0. I'm going to come back and explain why here in just a moment. All right, PE2. The height I need for the second potential energy, I'm going to put this one in green as well, is this height. And that's basically equal to the length of the rope. So the PE2 term we can write as minus mgl, and again minus because we're below the datum. And then the KE2 term, 1/2 mv squared. All right, let me talk about that work term again and why that's 0. That's a really important thing to realize. And to do that, I'm actually going to draw that object one more time. So you notice I draw lots of pictures. Now I'm gonna draw a free body of it somewhere in this part of the path, just kind of a generic free body. The first force I'm going to put in that free body is the tension, which is going to act this way. And I try to draw this force vector smaller than this one because I know from observation it's going to be less force. Another force acting on it is the gravitational force. Straight down. mg. And that's pretty well it. Those are the only forces acting on this object at this instant. Remember, forces come in two types. You got field forces and contact forces. There's a field force, gravity, acting at this instant. There's a contact force because of the string. And that's it. There's nothing else in contact with this object, at least if we throw out air drag, which is not an important force for this problem. Now, let's ask ourselves, does the gravitational force do work as this object moves along this path? And the answer to that is yes. At this instant shown, this force does have a component in that direction. However, that's what these terms are taking into account. The potential energies are taking into account the work done by gravity as we move along this path. Next question, does the tension do work? And the answer to that is no. And the reason is because at the instant shown, the velocity is this way. and the velocity makes a right angle to the tension. And that's true. You can see it in this picture really clearly. The velocity is to the right, the tension's up. But it needs to be true the entire path, and that's why I drew this kind of intermediate picture to show that no matter where we are along this path, the velocity vector is going to make a right angle to the tension. So the tension does not do any work as this object moves along this path. So we've considered both forces. Gravity is taken into account here and here. The tension is not doing work. That's why that thing is 0. Right? What we have here now is an equation that's pretty easily solved for the v, or actually what we need is v squared. So let's see. We can add this to the left, and that's going to give us mgl minus mgl sine theta, or sine 40. It's my shorthand for sine 40, equals 1/2 mv squared. Now you notice there's a mass in each term, and I can multiply both sides by 2. So the next line is going to read 2gl minus 2gl sine 40 equals v squared. So now, anywhere we see a v squared, we can put this. And I'm going to go ahead and shorten that up a little bit. Notice that you can factor out a 2gl. So 2gl, and what we'd be left with would be 1 minus sine 40. So now what we can do is take this expression that we found and sub it right there. I'm going to do that and rewrite to that equation. So our tension is going to equal mg plus m, okay, now times v squared, which is equal to this, 2gl times 1 minus sine 40 over L. And you notice that these divide out. So I'm going to go ahead now and write this out, and take note that the units are consistent, so I'm going to run out of room. I'm going to leave the units out, so note consistent units. Okay, so mg is going to be 10 times 9.8 plus, oh boy, I'm probably going to need a little more room. I'm going to take a moment here, and this program's really nice for stuff like this. Just make myself more room. All right, so mg plus, this is 2mg, so I'm going to go ahead and write that 2 first, the m, the g, and times 1 minus sine 40. Equals. And let's see what we get out of that. Hopefully I did this right. I got 105 newtons out of this. I'm going to run that again because I'm not sure I trust that. Ooh. And I get 168 second time around. So that tension is looking like approximately 168 newtons. That one I think I trust. Let me talk a little bit about how I knew almost instantly that that one was wrong. All right, just by observation, I know that the tension's got to be larger than the weight, and the weight is mg, with m being 10 and g being 9.8. So I knew that this is right around 100. I knew that 105, that wasn't going to quite cut it. I know that's slightly a lot higher than 98, but my gut told me that force was going to be quite a bit higher than that. I believe the 168. Hopefully it's right. So, again, let me go over the highlights of this problem. So this thing's, again, this mass is, kind of imagine it kind of going back and forth. Its speed would be at the highest at the bottom, and that's pretty much why the tension is largest at this position. To find the maximum tension, I drew a free body diagram at this position, which had two forces. One is kind of covered up in green here, but that black force vector here was the tension. Notice too, by the way, that I don't bother to draw that tension like ending at this position. I see that a lot in people's homework. The length of this rope is not relevant to the length of this force vector. They're different things. So the tension is up, the mg is down. Those are the only two forces acting. So the first thing we really need to understand how to do is draw that free body. Second, we need to know how to write a Newton's second law equation for it. The acceleration is up basically by observation, because we know it is a centripetal acceleration that's always towards the center of curvature, which is here. That makes the relevant Newton's second law equation, T minus mg equals mv squared over L. To get the v squared, you can write a work energy equation between position 1 and position 2, which I did, using this blue line as my datum. You can put the datum down here. You'll end up with exactly the same thing, 168 newtons at the end of that. You could also put the datum here if you wished, and again, you'll end up with exactly the same thing. Generally speaking, usually when I've got something rotating about a point, I usually put my datum at the rotation point. But there's the relevant work energy equation for position 1, position 2 with the blue datum. The rest of this problem is really solving for algebra, a pair of equations here, and here. Solving this equation, for this one right here, for v squared, subbing into this. So again, the purpose of this video is to give an example of how to draw free bodies and apply Newton's second law for a circular motion problem. I hope this helps demonstrate that for you. Have a great day.